Hello, everybody. Are you guys able to see the screen and to hear me?
Yes, sir.
Excellent. Great. So welcome, everybody, to Concrete Design. I will be your professor for this next 10 weeks. Make sure everybody's in the right place. This is CE 4510, Structural Design Reinforced Concrete. And so if you guys can see my screen, then let's get started. I like to start with kind of walking through the syllabus so that everybody knows what to expect. I guess first things first, my name is Aaron Pratt. And pardon me as we got a few stragglers coming in here. So my name is Aaron Pratt. I'm a practicing structural engineer. I work for a company called Clark Pacific. We do precast concrete elements, a lot of parking garages and precast buildings. And I head up the structural design department of our company. I have been working here, let's see, just passed up 26 years. I've been working here. I am a graduate of Cal Poly San Luis Obispo, and I got my master's degree at Cal Poly at Pomona. So that's a little bit about me. And I'm a licensed structural engineer. So that's a little bit about me. Again, my day job, my real job, is working for Clark Pacific. I do some teaching for Cal Poly as a side job, a hobby, if you will. I guess adjunct professor is what you'd call me. So that's who I am. If you need to reach me via phone or text, my number is listed here, 909-342-2797. Particularly that comes up during this whole virtual thing if somebody has a problem with one of the exams and they need to get a hold of me, texting to that number is probably the best way. If you want to email me for whatever reason, but if you have questions about the class or questions about the homework, whatever, if you want to email me, I would suggest emailing me to the address you see here, the epratt@clarkpacific.com. That is my work email that is constantly being monitored both by my computer system here at work and on my phone. I do periodically check the CPP email address, but that's not very reliable. And I get no notification whatsoever if somebody email me to the CPP. So I would suggest if you want to get a hold of me in a timely manner, do it through the epratt@clarkpacific.com. We're going to have office hours between 4 and 5 p.m. on Tuesdays and Thursdays. So basically the hour before this class will be the office hour. I posted a separate invite to a Zoom meeting for the office hour. And typically what I'll do is I'll log into that Zoom at 4 o'clock. If nobody's on there by 4:30 or so, then I'll log out of it and go get a bite to eat or something before I come back to teach the class at 5 o'clock. But if you're never going to be late and you want to talk to me through the office hour, no problem at all. Just send me an email and let me know about what time you think you'll be on. So apart from that, so that's how you get a hold of me through text, how you get a hold of me through the email, the office hour. So required texts for the class. I think can you guys see me in a little window? So this is the textbook for the class. It is Design of Reinforced Concrete by McCormick, and it is the 10th edition. The 10th edition is important because it's been updated to the most recent code that we're using now, ACI 318-14 code. So it's important to get the right textbook that has the right references. This textbook is mandatory for the class, and you're really, really going to need it to take your exams. The exams will be open book. Okay, apart from the textbook, I strongly recommend that you get a hold of this standard. This is the ACI 318-14. This is the Building Code Requirements for Structural Concrete and Commentary as published by the American Concrete Institute. And we're going to be doing a lot of referencing to this book. This is basically the design Bible for reinforced concrete design. All reinforced concrete design in America and elsewhere follows this book. Your building codes reference this book, so they're not reproduced in the building code or duplicated in the building code. They just reference this book. So this is the book that we design reinforced concrete buildings to. As I said, going through this class, the textbook will reference this book a lot, and my lectures are going to reference this textbook or this code book a lot as well. Just mainly for the point of where do you find things in this code? This code has ballooned up to 500 pages now. So it could be challenging as to where do you find the exact provision that says you can or cannot do something. I will be referencing them in my lectures, and so it'd be very good for you to have this book. Any questions so far? Okay, this class is scheduled from 5 to 7:05. And I propose that for a 2-hour class, we're going to take like a 10-minute break in the middle. So basically from 6 to 6:10, each lecture will take a little break. So that's the schedule of the class. And this is summer course. Welcome to your glorious summer. This is the summer course, so it's abbreviated. Well, it's not abbreviated, it's just condensed. So we're going to go through a lot of stuff relatively quickly. This is basically all of the topics covered in a 16-week semester, and we're going to do it in 10 weeks. So starting with tonight is probably going to be the only light and fluffy lecture that we have. They get rather intense after this. So tonight is just an introduction, after which we're going to, and you can see the chapter references there, chapter 1, chapter 2, chapter 3. Please keep up with the reading. It is very important to understanding this course to go through the reading as we go through this course. So they start off rather quickly. Chapter 1, you should hit tonight, this weekend, chapter 2 and chapter 3 next week, so on and so forth. We're going to go through the topics of basic mechanics of concrete design. Then we're going to jump into strength analysis of beams, strength design of beams. There is actually a difference between analysis and design. And then one-way slabs. Starting in the 4th week, we're going to do analysis of T-beams and doubly reinforced beams. Then we're going to, at the end of June, we're going to jump into shear design and then deflections and cracking. July 6th is a TBD, which is a catch-up day. And then please note, July 8th is our midterm. The midterms have to be taken between the 5 and 7 o'clock hour on the day that they are listed. So please make arrangements, make sure you're not in Tahoe on July 8th for that midterm. After the first midterm, we have introduction to column design, the design of short columns. We have slender columns. That's a pretty big topic. It's continued on the 22nd. July 27th, we start talking about bond development of reinforcing bars. and then we get into footings. August 3rd, we'll kind of talk about retaining walls, and then we have a TBD again, a catch-up day, and then on August 10th, that's a Tuesday, is the final exam. And again, the final, just like the midterm, has to be taken at the time and day as shown. So please make sure that you're available at that time and day. What else do we have? That's it for that page. I will be recording each one of these lectures. So if you don't want to be recorded, you don't have to verbally talk during this, but I've had several requests to have the lectures recorded, so I will do so. And then probably the next morning after the lecture, I'll post the recording to YouTube. To find my lectures, basically just type in my name, Aaron Pratt, and then type in CE 4510 or engineering or whatever. You'll see there's quite a few videos already posted there. And you should find the lecture that you're looking for. There are also, if I remember right, from last summer, I recorded each one of these lectures too. So they kind of get like a double. If you wanted to sit through two versions of the same lecture, there's lectures from last summer as well. Okay, grading for this class. Homework will account for 20% of your grade. The homeworks will start on our next class meeting on June 8th. I'll post homework number 1, and it will be due a week later. So homeworks will be due each Tuesday, starting on June 15th and going through basically the last Tuesday that we have in the class. As you can see there, we're going to have 8 homework assignments through this course. So the homeworks are graded, and they are worth 20% of your grade. The one midterm is 40%, and the final is 40%. All exams are open, class-assigned textbook only, and you're allowed a single page, 8.5 by 11 of notes will be allowed. The notes must be handwritten, no pictures, no printed material, no examples, and most certainly no work from when this class was taught before to be brought into this class. We are in hopefully the last time, but we are still in the virtual world. This entire class will be done virtually on Zoom. And so the midterm and the final will be taken via Zoom and Blackboard. All of your homework, by the way, is to be turned into Blackboard. And I'll go through, as we get closer, I'll talk about how we do the midterm and the final, how we work those out and do those through Blackboard as well. So yes, there's a little bit of an honor system here. I can't actually watch you take the midterm and the final, but please understand that the understanding is you are expected to only have in front of you a textbook, a single page of handwritten notes that you have written yourself, a calculator, a pencil, and your paper. And that's it. That's all that is supposed to be in front of you as you're taking your test through Blackboard. The one page of notes will be turned in with your handwritten work with the exam. And my basic rule is any compromised tests will not be credited. You basically, if there's obvious, or it doesn't have to be obvious, if I find evidence of cheating, then the test will be graded at 0 points. No makeup exams will be allowed. Okay, any questions so far?
Professor, so to clarify, one midterm and one final only.
That is correct. One midterm on July 8th, and the final is on August 10th. Okay. Actually, I did make a change in my policy. If you read on the syllabus, it says that the homework is due on the date given by 5:05 p.m. I've extended that in this virtual, and you'll see it when I post the homework assignments. You will see that each homework assignment is actually due at midnight of that Tuesday. Again, you can see on the syllabus, every homework is due on Tuesday, but I extended it to be midnight. That way, give you a little more opportunity during that Tuesday lecture to ask some more questions or get some clarification before it's due at midnight. Late homework, if you have a good excuse for why your homework is late, then I will accept late homework for half credit. Is that a link to where you can buy the book or check out the book?
No, it's the actual book where you can download.
You can download the textbook?
Yeah,
No
10th
kidding.
edition, right?
10th edition, yeah.
Yeah.
Thank you, sir.
Yeah, I bet the bookstore doesn't appreciate that, but
Yeah.
okay. All right, how about that? All right. And then the last thing I want to say about the syllabus is that I think we've all been asked to share that the Learning Resource Center offers tutoring help. And I am not exactly sure how this works during the virtual environment, but those are the room numbers, building 15, rooms 2921 and 2919. They have a phone number that you can reach them from Monday through Thursday. They have an email address that you can send to them. But I've been told that there are tutoring services to help if you need any help with that. And finally, the prerequisites for this course is that you must have passed the CE 3501 class. Okay. Any questions at all about the syllabus or what we plan to do in this summer course? All right. This is posted on Blackboard, so you can download it and take a look at it at your leisure. All right, so let's start with tonight's lecture. Usually the first lecture, I allow more time because you guys don't know me and this is all brand new and all that. So I allow lots and lots of time for questions. Please do not be shy. You can ask questions verbally at any time. You can interrupt me. In fact, I encourage you to interrupt me with your questions at any time, or you can use the chat function, which I kind of see out of the corner of my eye, and I'll address things like that as well. If you have a question that you do not want everybody to know who asked that question, then just send me a private chat. I see it, nobody else sees it. I'll answer the question, hopefully without revealing who asked the question. So that's available to you as well. Okay, so let's do a brief introductory to the material of concrete and the world of concrete design. Okay, so let's start with our materials. Concrete is made of, well, let's see. Does anybody know? I gave you the first one, sand. What are the constituent properties of concrete? What are the ingredients? Water,
Aggregates.
Okay, sand, water, aggregates, cement, very important. And so there's your coarse aggregates, your fine sands, water, cement. What's the fifth one in our modern day world?
Admixtures.
Admixtures, thank you. That's right. And we have admixtures. So these are the basic constituents and ingredients of concrete. Of the sand, we have what's known as regular weight, and we have lightweight sand. And I can tell you in my experience, I have never actually used lightweight sand. I'm not even sure where you can get lightweight sand. I bet you it's pretty darn expensive. We have exclusively used regular weight sand in all of our concrete mixes here. Your aggregates, coarse aggregates, you can have regular weight aggregates and you can have lightweight aggregates. We do use a ton. We probably use a ton a second. We use a lot of lightweight aggregates and a lot of regular weight aggregates as well. The lightweight aggregates can be of the expanded shale, clay, or slate flavor, or they can be made of a natural material such as pumice. The ones that we use here are basically expanded shale is the one I have experience with. And I believe we buy ours by the railroad car from Salt Lake City or in Utah someplace. And one of the things that we'll get into later is with lightweight aggregates, your shear capacity is actually reduced. The lightweight aggregates don't have quite the properties to protect against shear as regular weight aggregates. Okay, water and cement together form this thing called a water cement ratio, which is by weight, right? So you take the water and you figure out if you have so many gallons per yard of concrete of water, so many gallons of water weighs so many pounds. So you take the pounds of water divided by the pounds of cement to give you a ratio. The lower the water cement ratio, the more strength you could expect to see in general. The higher the water cement ratio, the more workability you could expect to see. Okay, so that's kind of always the balance. You could put like a 0.32, 0.3, 0.32, 0.34 water cement ratio, and you'll get fabulous strength, but that doesn't do any good if you can't even pour it into the mold because you have no slump, right? So there's always this balance between having a low enough water cement ratio that you get the strength that you're looking for, but having a high enough water cement ratio that you can pour it into the mold and vibrate it and work it and trowel it and all the things you need to do to get a good looking product. Or you may be using this in an application where you have to pump the concrete, in which case you actually need a little bit more of a slump. So you need a higher water cement ratio so that you can pump the material to where the material needs to be placed. So the water cement ratio is also associated with slump. Slump is a measure of the workability, right? So all of you, have you taken a concrete lab where you actually had to make cylinders and measure concrete slump? Is that familiar to you guys?
Yep.
Yeah.
Okay, great. So, and now of course we also have, well, I'll get to it in a second, but the water cement ratio also affects shrinkage and creep, right? So the higher, we did the lab virtually. Oh, I'm sorry. How do you do a lab virtually? How did that work out?
Just a video.
Yeah,
Oh.
YouTube video.
Professor Lynch, he would show us videos of how it was done.
Okay. All right. Well, I guess, we all had to do the best we could, but oh, that's a shame. I mean, there's nothing like actually getting your hands dirty and shoveling cement and stuff. But anyway, okay. So you did it virtually. The water cement ratio also affects this property called shrinkage and creep, which is a kind of a unique property of concrete in that all concrete, when you pour it, it's a wet concrete mix, right? It's pourable. And then once it cures, not necessarily dries, but once the concrete cures, it's releasing a lot of that water into the atmosphere. So a lot of the water that's in the concrete is not actually needed for the hydration process of turning wet concrete into solid concrete, but a lot of the water is there just for workability. And that water is released over time back into the atmosphere. Well, as the concrete and what we call the matrix is actually the cement paste with all the sand and aggregates kind of glued in there. That's the matrix. And as the matrix gives up the water, the whole thing shrinks. Also, if you have concrete that is under a sustained compressive stress, it also shrinks. But we separate the effects of shrinkage, which is due to just water evaporating basically, and creep, which is water being squeezed out of the concrete. We separate those into the two separate effects so that we can kind of get our hands around them. But really, it's the same thing. It's that the water is being expelled from the concrete, so the concrete shrinks. And at this point, basically all I want to say is that the lower the water cement ratio, the less creepage and shrinkage you will see. The higher the water cement ratio, the higher the creep and shrinkage that you will see. Okay. So a really low water cement ratio, something like a 6,000, 8,000 PSI concrete is really dense, and it will have far less shrinkage problems than like a 2,500 PSI concrete mix that you might use for a driveway or a sidewalk. That mix is going to be a lot cheaper, but you better put in crack control joints and all that because it's going to shrink. Okay, so that's a little introduction to water cement ratio. Of course, all of these properties, strength, workability, slump, shrinkage, and creep, can also be modified by using admixtures. In other words, you can keep the water cement ratio fairly low and then get your workability and slump back by putting in plasticizers and super plasticizers and water reducers and things of that nature. Okay, which I'll get to in a moment. So the cement, the actual cement that goes into concrete, there are types 1 through 5. Type 1 is the common all-purpose cement. Type 2 has a lower heat of hydration than does type 1, which might be important in certain times. And it is known as a medium sulfate resistance. Sulfate attack is like alkali attack. If you ever see concrete like on an overpass or at a freeway and it's just like has all these cracks, spider cracks everywhere, and it looks like it's just kind of falling apart, that could be a sulfate attack. It could be from de-icing salts on the roadway, could be from just acid rain or stuff in the atmosphere, all kinds of reasons for it. But type 2 has a better sulfate resistance to concrete deterioration than does type 1. Type 3 is a high early strength, something that we take advantage of in the precast world because we need a lot of concrete strength in a number of hours, like 14, 16 hours, and we need 3,500 PSI to keep the operation moving every day. But there's other situations where you might need high early strength as well in your concrete. Type 4 is a low heat of hydration. I think this is even lower than type 2. And this is something you would specify for large structures. What comes to mind is like the Hoover Dam. something like that, where you have a tremendous amount of concrete curing in a giant mass pour. So like the Hoover Dam, or like a mat foundation, one of these big buildings that gets like a 6 to 12 foot thick mat foundation. So if you don't specify low heat of hydration in these mass concrete pours, then all that concrete curing at the same time can actually elevate the temperature and degrade the quality of the concrete if it gets too hot. And type 5 is what's known as a high sulfate resistance. So if you really feel that you're doing concreting in a place that is susceptible, like something that's close to ocean spray, which is really kind of curious. If you do concrete that's in the ocean, that's not so bad. If you do concrete that is above the ocean, that's kind of bad. But if you do concrete that is right where the ocean meets the atmosphere, that's really, really bad. So just so you know. Admixtures. Okay, so we have these general categories. There's a zillion billion different kinds of admixtures, but we have these basic categories. One is air entraining admixtures, where just the process of mixing and batching concrete, you have what's known as entrained air. And they're almost like microscopic or almost microscopic little bubbles of air in the concrete. And all concrete has them to some degree. We found that our hard rock mixes will have something like 1 to 1.5% of air. So 1.5% of the whole batch of the volume of concrete is actually air. For our lightweight mixes, we find we get more like 4 to 5% air, and that's without using air entraining admixtures. If we put air entraining admixtures in there, then you can get whatever the design calls for, 5%, 10%, even more. But more than about 8%, I'd say you start seeing some dropping of your strength. So thank you, Eric. That's exactly what I was going to ask. Why would you want air in your concrete?
Moisture.
What about it? What about moisture?
So there's room for moisture whenever there's like freezing.
That's right.
Then it melts and it allows to some expansion for the moisture.
Exactly. Yes, that's probably the main reason I've heard of using air entrainment. And you want something like 6% air if you have something that is exposed to freeze-thaw cycles, is what they call it. And that's exactly right. There's always going to be some water on or in the concrete. Having these little air bubbles gives the water some place to go when it expands, when it freezes. And so it gives it some protection against that. That's really the main reason that I've heard of using air entrainment, is stuff that is exposed to freeze thaw. So what's the problem with air entrainment? I kind of alluded to it. What would be the problem if you get too much air in your concrete?
Your concrete will be like hollow inside.
Your compressive strength will start to suffer. And at first it doesn't affect it very much, but then you get to a tipping point and it really starts to drop your concrete strengths. So that's why you don't want any more air entrainment than what you need to do the job to protect it from freeze thaw. Okay, we have what are known as accelerating admixtures that basically accelerate the curing process, right? So accelerating admixtures will help it to cure faster. And again, there's times, especially in the precast world, when You need the strength quicker. There's many times in the world of concrete, it doesn't really matter. You can wait, doing foundations or doing walls, columns, whatever. Sometimes it doesn't really matter. So there's no sense in spending the money to buy that. But in other cases, it matters a whole lot. Like if you're doing a high rise and you can't go to the next floor until you get a certain amount of strength in the floors below, then using accelerators really helps you out because you can jump more floors in a period of time. So it just depends on the construction schedule and what's going on. We have the opposite. We have retarding admixtures. And why would you want to do that? Why would you want to retard your concrete?
For transportation and logistics.
That's a good reason. Yep. You might want to retard it because of the anticipated time that's going to be sitting in the truck, and you don't want it to start firing off while mixing in your truck. That's a big problem. You could also have weather constraints. You could have hot weathering, hot concreting. And again, the hot weather will tend to make the concrete fire too quick, and you can't get it to pump and place and finish properly because it's curing too quickly. So you could use it for those purposes as well. We have super plasticizers. These are basically admixtures that allow you to use a lower water to cement ratio and still get enough slump that you can pump and you can place and vibrate and finish properly. My understanding of super plasticizers is that they're basically like vegetable oil. You put a little bit of vegetable oil, not literally, but you put this stuff in there that's like a vegetable oil, and it lubricates the friction between the aggregates and the sand and the cement itself. So it's kind of lubricating everything so that you have basically the same effect as if you're putting more water in it, but without the strength degradation that you get from putting in more water. We could put waterproofing materials into our admixtures, and that's pretty much what it sounds like. It basically makes the concrete more water resistant. And those are the ones I had. Any questions about admixtures?
In your work, Professor, do you always use this, or is there any chance that you don't add at all?
That's a good question. Yeah, no, in our work, we pretty much always use some of these, always. Yeah, we never pour concrete that has no admixtures in them at all. And we still consider ourselves pretty old school in the way that we do it. We still use, and I didn't talk about, wonder if it's in my phone coming later, but a lot of concrete these days will use a certain percentage of pozzolans, which are like fake cement, right? So we have things called fly ash and slag. There's a few others that you can use. And basically up to a certain percentage, like 10 or 15%, they fool the mix into thinking that it's cement when it's really not cement. And of course, fly ash and slag and those elements are much cheaper than the cement that they're replacing. So like a lot of cast in place or ready mix type companies will use those because they control the cost of the mix. I mention that only because we're old school. We don't use fly ash or slag or any of those pozzolans. We just use a whole lot of cement. And it's worth it to us to use the cement because it gives us high early strength and very dense concrete when we want it. But we do always use, at the very least, this category here, the superplasticizers. A little bit of superplasticizer replaces a whole bunch of water. And anytime that you can get the workability that you need while not using any more water than you have to is always a good thing, because we're always looking for 6, 7, 8, sometimes 9,000 PSI concrete, which is quite a bit stronger than the typical cast in place building would be specifying. Typically, cast in place buildings are looking at the 4,000 to 5,000 PSI range. So we achieve that by a whole lot of cement and using superplasticizers. That's a good question. Any other questions on this so far? Okay, so let's talk about concrete testing. So concrete is designed to a specified strength, and we're going to become very, very familiar with this nomenclature, but it's called F prime C. F prime C is the symbolic way of illustrating or communicating what the designer of the building or the element, what the designer was assuming you are going to use as a minimum strength of concrete, right? So we as designers, we as the structural engineers are going to specify on our drawings F prime C equal to 4,000, 6,000, 10,000, etc. But we're going to pick some modular or nominal strength of concrete based on the needs of the project that become the specified strength. So that's what F prime C is. And you'll see this throughout this course. You'll see it in the code book. You'll see it in the text. F prime C is always the structural engineer designated required strength of the concrete. So for example, if I specify that the concrete I'm designing has an F prime C of 6,000 PSI, then it is incumbent upon the general contractor or the concrete sub or whoever's in the field who is contracted to provide that concrete, it is incumbent upon them to get me 6,000 PSI concrete, right? They can give me more than 6,000, but they really can't give me less than 6,000. 6,000 is the minimum that I require for this building to perform the way that it was designed to perform. Okay, so does that make sense? So F prime C is the design value. What you actually get in the field had better be more than F prime C. And then I'll cover in a second how you do that. So F prime C for concrete, really structural concrete kind of starts at 3,000 PSI. I think the code might allow you to go down to 2,500, but I wouldn't do anything that's over my head at 2,500. Minimum is really kind of 3,000. 2,000 or 2,500 is really more what you would expect to see, like I said before, for driveways or sidewalks or something that's essentially non-structural. 4,000 is pretty normal. 5,000 is getting to be a little high performance on cast in place structures. 6,000 in some jurisdictions is known as high strength. Certainly 10,000 in all jurisdictions is known as high strength. And they're doing some really wonderful things these days. 15,000 was a number of decades ago considered to be unattainable. Many concrete producers will get 15,000 on a regular basis. But this is where it gets interesting, is about 10 to 12,000 becomes regional. So in other words, after, I don't know, maybe 9 or 10,000 PSI, your concrete starts becoming limited by your natural materials. So there's regions of the country that can regularly get 18,000 PSI concrete because of the aggregates that they have are very, very strong. There's other parts of the country where getting 7 or 8,000 PSI is really a challenge because of the quality of the natural aggregates, right? And it's very, very expensive to transport aggregates. Sure, it can be done, for like a special project, but generally you're not going to ship all the aggregates you need for a building from, say, Seattle to Los Angeles. You just don't do that. You design with the natural aggregates that you have around that area in general. But then you do have some very special buildings like the Burj Khalifa, right? Currently the world's tallest building, which I understand had 15 to 18,000 PSI concrete on it. And they had to do a lot of really special things to get that strength of concrete. Okay, so anyway, that's what F prime C is. That's what F prime C stands for. It is the design minimum compressive strength of the concrete. So how do you know when you're actually pouring concrete that you are getting concrete that will meet the design? And the standard way to do that is to do field testing with concrete cylinders. And again, all of you guys who have taken the lab virtually or otherwise know what I'm talking about. You took concrete cylinders, you cured the cylinders, and you crushed them in a compression machine to see what the strength of the concrete was, right? Everybody's had that experience?
Yeah.
Okay. So that's what we do in the real world. You still have your cylinder, cool. In the real world, you go out and you take cylinders from the wet concrete. They will sample the concrete before they dump it into the forms or whatever. And they take cylinders. The cylinders most commonly are 4x8, so a 4-inch diameter by an 8-inch height on the cylinder, or a 6x12 are the most common. When you are designing a concrete mix, not checking it in the field, but when you design a concrete mix, batch plants will mix trial batches, right? Whether this is a ready mix company or a precast company like ours, we all go through the same process. We design a mix, we think this is going to work pretty good, but we have to batch up trial batches. And because the trial batches are a limited sampling, right? Remember from statistics, you have the whole population and then you have a representative sample of the population, and you have to do some statistical analysis on that. So generally speaking, you do 30 tests if you are a batch plant that's trying to get a new trial batch passed. You do 30 tests. And the definition is each test is either 2 6x12 cylinders or it's 3 4x8 cylinders. Okay, so you're doing somewhere between 60 and 90 cylinders to qualify a batch, a trial batch. And then what you do is you break all 60 or 90 cylinders and you get an average, and you get a standard deviation of those averages from all those breaks, right? If you break 60 or 90 cylinders, you're going to get a little bit of a range from the low to the mean to the high. All right. Well, depending upon how much that range is spread out, but what the code says is that the trials, you have to average this F prime CR at above the design strength. So again, if you're trying to get a 6,000 PSI, then you need to get this F prime CR equal to or greater than 6,000 PSI. And the F prime CR is equal to this. if F prime C, if you're shooting for something that's equal to or less than 5,000, then F prime CR is equal to F prime C, the design that you're shooting for, plus 1.34 times S sub S. S sub S is the standard deviation of all these 60 to 90 cylinders that you tested, okay? So it's the greater of these two. It's either the design mix plus 1.34 times the standard deviation, or it's the design mix plus 2.33 times the standard deviation minus 500 PSI. Whichever of these two is the greater, that's what you need to get in your trial batches on average. If you are designing a mix that is greater than 5,000, like my 6,000, for example, then your F prime CR is equal to the design mix plus 1.34 times the standard deviation, or 0.9 times F prime C plus 2.33 times your standard deviation. So as you can see, the higher the fluctuation of your standard deviation, the higher your standard deviation is, the higher the trial batching average has to overperform from the design mix that you're trying to get, okay? So I've done a few of these, and when you run the numbers, if I'm trying to get a 6,000 PSI, F prime CR may be like 6,800, or it may be even 7,200. So all these 60 to 90 cylinders have to average out higher than, say, 6,800 in order for that mix design to qualify as a 6,000 PSI concrete mix. Okay, so this is how it's done on the producing side. When we produce the concrete, we are fairly assured that the concrete's going to perform by this statistical analysis way of designing the mix design. On the inspection side, site testing side, then the site testing will be considered acceptable if the average of 3 breaks is greater than the design, right? So I break 3 cylinders and the average is greater than my design of, say, 6,000. And if the design is less than or equal to 5,000, you have no one breaking cylinder less than the design minus 500 PSI, okay? So say like you have 3 cylinders and your design is 5,000, right? And one cylinder breaks at 53, one breaks at 57, one breaks at 4,900. That's going to be okay because the average of those 3 is going to be more than 5,000. And even though one broke at 4,900, it did not break less than 5,000 minus 500, which would be 4,500. So by that criteria, that mix is, or that batch is okay. And so the site inspector would write down the findings and put it in a report, and everything is okay. If the 3 breaks does not meet F prime C on average, or you do have one break that is lower than the design minus 500, then the site inspector would write a non-conformance report and say, hey, we got some issue with the concrete here. If the design mix is greater than 5,000, then you need to meet the 3 breaks greater than the average, and you cannot have one break that is less than 90% of F prime C. Okay, so any questions there about, I mean, we talked about the design strength, F prime C. We talked about this F prime CR that you have to achieve while designing a concrete mix. And we talked about field inspection for conformance of that mix to the design documents. Any questions about this aspect? Everybody okay with this? Okay, so it's 5:55. This is a good breaking point. Why don't we take like a 10-minute break? This is what I plan to do for each one of these classes. So let's come back at 6:05 and we'll pick it up from there until we get to the end of this presentation. So everybody stretch your legs, get something to drink, and I'll be back in 10 minutes. All right, I am back. Everybody still here?
Yes.
Thank you. All right, so let's get going. I just thought it'd be interesting for a minute to kind of talk about what happens. What happens if the concrete on the building does not come up to strength? What if you did your 3 averages and it's still below the design strength, like significantly below? What happens?
Wait,
Anybody?
can you repeat the question?
Okay, so we talked about how to do field testing. And we talked about how if 3 cylinders average higher than the design strength and no one cylinder is less than the design strength by 500 psi or 90% for the higher strengths. But what happens if you do field testing and it doesn't meet that criteria? You really do have concrete that did not come up to strength. What then? That's funny.
A lawsuit?
Yeah, that might happen too. Yeah. Well, there's a few options. There's kind of like a cascading, from bad to worst to worst. The first thing that you would do is maybe test some more cylinders. Maybe you just had a bad cylinder and do another batch of cylinders and see what you got. Another option is instead of basing your decision on 28-day strength, if you still have some cylinders left over from that batching, you can wait until you have 56 days. And sometimes it will grow in strength enough between 28 and 56 to meet the design. And that's fine. Most designers will say, all right, well, let's just wait another month and see what we get. If you're still not getting there, ACI, the code, will allow some field testing where you can core the concrete that you've already poured, and you core the concrete and pull out cylinders of concrete from the actual building, and you can test those. And there's some criteria to that. But if that doesn't make it, now you're going to the next step where you have to go back to the structural designer and say, well, I know you wanted 6,000, but can you live with 4,300? And the designer, a good designer will go back and check the calcs and check the performance criteria and everything. And they'll either say, well, in this case, yeah, I guess that would be all right. Or they'll say, not a chance. No, fix it. If you get to the point, rebound hammer test. Yeah. But that's not quite as accurate. I don't think you can convince anybody with a Schmidt hammer or a rebound hammer to save or not save concrete. Basically, you need something a little more, and pardon the pun, concrete, to show that you have the strength. And you can also, there's some provisions for doing some load testing that's in the code to justify what you have. But if you really do have something that's critical, like a column or a shear wall or something, and the concrete just never actually made it. It happens, every once in a while, a mistake is made and it just doesn't work. Then you have to start looking at how to retrofit it or how to fix it. And the absolute worst case is tear it down and start all over. And it's rare. It's really rare, but I've seen it. It wasn't low strength that I actually saw. It was a parking garage, a concrete parking garage down in San Diego, and the we were putting precast on the garage, but the shear walls were all cast in place. So the cast in place, the concrete sub had to do his work first, and then we come in and build around the shear walls that he built. And he built this shear wall that had such bad consolidation in it that it had a, like, it looked like a crack, but it was actually like a 20, 30 foot long by 12-inch high section of concrete that never got any concrete. It was just a giant window through the shear wall. It just never got any concrete. And they went to the engineer record and said, well, you know, we know we messed up, but can we save it? Can we patch it? Can we just fill it up with some grout or something? And the engineer's like, no. And they tore that wall down. It was maybe like 30 feet long, 35 feet tall, big concrete, you know, 24-inch wide, thick, and they tore it down and had to start all over again. So it does happen. Okay, back to the presentation. Let's see, where are we? Okay, so we're going to look at some stress strain curves for typical concrete, where if you remember from your mechanics of materials, stress strain curves, the stress is the vertical axis, the strain is the horizontal axis. So if I look at just a regular old watery 3000 PSI mix, what you notice is that as you are loading this concrete in compression, right, as you get to 1/1000th of an inch per inch strain, that you're about 2400 PSI. When you get to 2000ths, you've maxed out at the design strength of 3 KSI. And from there, it just starts degrading, right? So the more you keep compressing it, you don't get as much strength. It's basically on its way to just crushing or destruction. But it does sustain a fairly large strain, even though it's not carrying as much load anymore. As we go to a 4000 PSI mix, it maxes out at 4000, as you can see. It maxes out at about the same point, 002, but notice that it kind of falls off quicker than the 3000. Here we have a 5000. Same idea, it hits the maximum of 5 KSI at about 002 on the strain, but it drops off even quicker still, right? So what's happening is the stronger the concrete is, the less strain it's able to sustain. It becomes more brittle, right? So the lower strength concrete is more malleable or ductile, if you will. The higher strength concrete becomes more and more brittle. And 6000, same trend. So on the stress strain graph, what we're going to call this is between 0 and roughly 40% of the strength of the concrete is acting basically elastically. So that means the stress strain curve is basically a straight line in this range from 0 to 40% of the strength of the concrete. Beyond that, the concrete enters in what's known as a plastic range, where you have this kind of a parabolic or polynomial type of shape to it. And this comes in later for our strength design of columns and beams. So recognize that at the design strength of a column or beam, you're well into this plastic range, well outside of the elastic range. But if you're designing a concrete column or beam for serviceability, like cracking criteria or deflection criteria, then you will be in this elastic range. Okay, so that's why I'm talking about this. We have these two distinct ranges. The elastic range is used for checking serviceability, which is namely cracking or deflections or vibration. And we have this plastic range that is used primarily for checking ultimate strength. Ultimate strength is like the nominal capacity of the beam in flexure or in shear, whatever. But we have ultimate strength based on the plastic range, and we have serviceability based on the elastic range. This value here, the 002, is known as epsilon naught, and it varies a little bit, but it's basically where the concrete maxes out. It's the strain that corresponds to the tested maximum strength of the concrete. Okay, so epsilon naught is the strain where maximum compressive stress is reached. Epsilon naught is more or less 0.002 inches per inch. Okay, and then we have this epsilon C. And epsilon C is the assumed maximum usable strain. So epsilon C is the assumed maximum strain that is reliably achievable, right? So concrete may go to 4,000s or even beyond in these lower grades of concrete, but not always. And it's not really super predictable. So the code body, ACI, has basically just made a decision. We're going to design to 003. And basically all of these mixed designs achieve 003, but not a whole lot more. You'll find once we get to the design phase of this, it doesn't make a huge difference if you assume 003, or I believe like the Eurocode maybe assumes 0035, doesn't make a huge difference, but it does give you a benchmark, something concrete that you can design to. So for our purposes, for the purpose of this class, and for the purposes of anything governed by ACI, the maximum usable strain is 0.003 inches per inch. And that is documented. And this is how you're going to see this at least 1,000 times. But I'm doing this because you need to know where to find these things. So ACI 318, the 14 is the edition, the year that we're using. We are still in the 2014 edition of ACI 318. The 2019 is out. I have a copy of it right here on my desk, but it's not adopted yet by the legally binding code authority. Okay, so until they adopt the 19, we're still designing to the 14. This little curly killy dilly bobber thingy right there, that represents the section. So this is telling you it's in section 22.2.2.1. That's where you can find in ACI 318 where it basically legally tells you you have to assume 003. Okay. Then we have in the elastic range here, the slope of the stress strain curve is what's known as Young's modulus, right? So E sub C is Young's modulus for the concrete, and Young's modulus is assumed to be the slope from 0 through the elastic range. As you can see in the plastic range, the Young's modulus is really kind of meaningless because it's constantly changing the slope. Slope is even going downwards after a point. So it's only really meaningful in the elastic range from 0 to some point here where it's basically a straight line. Young's modulus is defined by the code as W sub C to the 1.5 times 33 times the square root of F prime C. This is applicable for all concrete densities. or in this equation, W sub C is the density of concrete in pounds per cubic foot. Got to make sure you got that unit right. And we can use Young's modulus is defined as 57,000 square root F prime C, which is the simplified version that is applicable to normal weight concrete only. And of course, Young's modulus, E sub C, is valid only in the elastic range. Now, another thing that you're going to find through this summer course here is that a lot of equations that are defined by ACI 318 have this square root of F prime C. That's a very common component of ACI equations. And really all it means is that a lot of this stuff is empirical. And they found that a lot of the empirical data fits very well to the square root of the strength of the concrete. It just is the best fitting function that's something based on the compressive strength of the concrete. But your units are going to get a little messed up here. So you have to know how to use units in the ACI world. The units of F prime C are either PSI or KSI, or if you're in the metric world, it would be megapascals. So the units of the concrete are PSI. So this would be the square root of 6,000 PSI. But the equations always assume that PSI is outside of the square root. Okay, so nobody's going to be looking for you to do 6,000, square root of 6,000, and then, oh, the square root of a pound over the square root of inches squared. It doesn't work that way, right? So if your concrete strength is 6,000 PSI, then the square root of 6,000 PSI is just going to be 6,000 to the 0.5. 77.5 PSI is what they're looking for. It's not going to be 77.5 square root of PSI. It's just 77.5 PSI. But you also have to know that when you have the square root of F prime C, you never use KSI. The square root of 6,000 is 77.5. The square root of 6, if you're trying to do KSI, the square root of 6 is 2.45. So if you took 2.45 times 1,000, you would get 2,450, which is very, very different than 77.5. Okay? So whenever you see the form of a ACI equation, and it's the square root of F prime C always has to be PSI. So this has to be 4,000, 5,000, 6,000. And the PSI is informally known to be outside of the square root. Okay, that was a little bit of a default detour there. Any questions on that? And yes, you will see plenty of examples in these lectures. Not tonight, because this is the light and fluffy intro, but after tonight, you'll see plenty of examples of how I do this actually. Okay, so Young's modulus is used typically for serviceability checks, deflection, cracking, vibration maybe. Concrete strength design is based on the plastic range of the concrete stress. This range here is the range we use for strength design. Okay, creep and shrinkage. Creep and shrinkage are both properties of concrete and water. Creep and shrinkage are both the expulsion of the water from the cement matrix, as I said earlier. So this is a graph that shows that this is strain over time. And you'll see that if you load something, you load something in concrete, you get this elastic portion of the curve, but then it keeps growing over time. That's creep and shrinkage. And you'll see that both the graph for shrinkage and creep have an asymptote, where it basically, the increase in strain over time basically goes to zero. It never actually gets to zero, but it gets really close to zero. So after, we generally use 5 years. So generally after 5 years, any increase in strain or deflection, anything like that, basically is done after 5 years. Shrinkage is the expulsion of water over time. Just due to the atmospheric, the water finds its way out of the concrete and eventually evaporates into the atmosphere. And shrinkage creates a reduction in volume. The concrete shrinks, obviously, but that shrinkage can cause cracking in restrained concrete pores, right? The most common example everybody's familiar with, pour a driveway or a slab on grade or the concrete floor of a grocery store, something like that. As you pour that concrete, it tries to shrink, but it's restrained either by columns or walls, or it could just be restrained by friction between the concrete and the substrate below the concrete. And so as the concrete is trying to shrink and it's being resisted from shrinking, that causes tensile stresses, which causes the concrete to crack. General rule of thumb is that all concrete cracks. There is no concrete structure on the planet that has not cracked, basically. So all concrete is expected to crack, but not all concrete is expected to crack uncontrolled or to the point that causes aesthetic or structural issues, right? So hairline cracks is one thing, big, hairy, scary, quarter-inch wide cracks, that's something else entirely. Creep is the expulsion of water under a constant stress. Creep causes an increase in strain under a constant stress. So again, they're both the same thing. We just separate the effects of shrinkage from the effects of creep because we can calculate them independently and then add them back together in our designs. Creep and shrinkage are most profound in days and weeks after casting, but will continue for years, again, following this type of shape. Okay, any questions on creep and shrink? Okay. Concrete tensile strength. In concrete design, compression is positive, tension is negative. I want to get this out of the way up at the very beginning here. I know that everybody has had a mechanics of materials class, and I know that in mechanics of materials, they teach you that compression is negative and tension is positive. And I know this because I just got done teaching it about 2 weeks ago. That's what we teach. That's the sign convention for mechanics of materials. Concrete design flips it. It is the exact opposite. And primarily because the concrete is only really good in compression. It's not very good in tension at all. So we look at the strength of concrete, whether we say it or we imply it, but it's really, we're always talking about the compression strength of concrete. So how strong is that concrete? Well, 6,000 PSI. Well, that you say 6,000 PSI. You don't say, oh, it's negative 6,000 PSI. No, you just say it's 6,000 PSI. But what you're inferring is that the compression strength of that concrete is 6,000 PSI. So that's just the nomenclature. That's the industry standard. We call compression in concrete design a positive stress. And if you have any concrete in tension, that's a negative stress. Okay, so that's the sign convention, and we're just going to stick to it, and we don't care what the rest of the world does. So when you look at a stress strain diagram for concrete, the compressive strain, right, is positive, not negative like in mechanics of materials. The compressive stress is positive, not negative like mechanics of materials. If you have some concrete that is in tension, then that's a negative strain, that's a negative stress. We have this measure of the strength of concrete in tension, where F prime C is the design strength in compression, F sub R is the design strength in tension. F sub R has a name for itself. It's called the modulus of rupture. And the modulus of rupture, F sub R, is equal to minus 7.5 lambda times the square root of F prime C. This lambda factor is a factor that varies from 1 to less than 1, and it's there to account for if you have lightweight concrete. Lightweight concrete cracks at a lower stress than does normal weight concrete. So we have this factor there, lambda, to account for that. Notice that the modulus of rupture is negative. So your answer to this is going to be, well, for 6,000 PSI, to the 0.5 times minus 7.5. So for example, normal weight 6,000 PSI concrete has a modulus of rupture about minus 580 PSI, which is not a whole lot. And then we have epsilon sub R, and epsilon sub R is a corresponding strain that we assume that corresponds to the modulus of rupture. Modulus of rupture occurs at epsilon sub R of equal to, remember, we're assuming we're in the elastic range here. So it's equal to the modulus of rupture, F sub R over Young's modulus. And it ranges anywhere from, what is that, 9/10 thousandths to, no, that's 900 thousandths to 15/10 thousandths inch per inch. So it's an order of magnitude less than the strain where you get the maximum compressive strength at say 2 thousandths inch per inch. Okay, everybody tracking okay, or am I going too fast?
Did you use 1 for the lambda?
I'm sorry, say again?
Oh, did you use 1 for the lambda?
I did, yeah.
Okay.
Okay, let's talk about shear strength for a minute, and I'll get back to that lambda factor here in just a moment. Concrete shear strength. So instead of compression strength, we've been talking about compressive strength. Then we talked a little bit about tensile strength. Now we're going to talk about shear strength. And in the world of concrete, the actual shear strength is actually very difficult to measure. Nor do we actually even care. The actual shear strength of concrete hardly, if never, controls the design. This is really kind of a weird concept, but concrete, even though we say we're doing a shear design or the concrete failed in shear, concrete doesn't actually ever fail in shear. What it fails in is diagonal tension. So concrete is much weaker in diagonal tension than it is in shear and will fail in tension first. Okay, so I don't know how long it's been or who taught it to you, but if you recall back to your mechanics of materials, if you recall the part of the course where you talked about stress and strain transformation, where you had this little cube element, right? And you have sigma x, you have sigma y, and you have tau xy. And so you can figure out that little element has so much normal stress horizontally, so much normal stress vertically, and so much shear stress on the element. And if you rotate that element, you can find at what angle of rotation you find the minimum principal normal stress, the maximum principal normal stress, and you can find where the shear stress is equal to 0 and where the shear stress is maximized. Well, the same thing applies in concrete, but what the weakest direction of concrete is tension. Concrete is much stronger in shear than tension, and it's much, much stronger in compression than tension, like 10 times stronger. So as you put stress into an element of concrete, it's going to find that angle of rotation where the normal stress in tension is maximized. And that's where it's going to crack first. So it's going to crack along a diagonal tension line long before it fails in shear. Yes. So a concrete shear wall is designed by whether it fails in tension or not. Yes, it does. Concrete shear walls don't fail in shear. I know, radical statement. 2 + 2 doesn't equal 4 anymore. But no, concrete shear walls don't fail in shear. They call it shear. We designed for shear. That section in the code is called shear design, but it's not really shear. It's diagonal tension. And we'll talk about this much more when we get to that section on concrete shear design. We'll come back to this topic. So, but what this means is, I'll get to that sec. So basically what it means is that we don't have any specification that says that the concrete needs to achieve a certain shear value. So like F prime C, there is no F prime V for shear. We don't care. We don't know what the actual shear strength of the concrete is, and we don't design to it. Likewise, there are no site testing there to do shear testing. There are, of course, ASTM C something or others. There are ASTM ways to test concrete for shear, but typically you wouldn't do it. You don't do that unless there's some very specialized laboratory requirement to test concrete in shear. We don't do it because we don't design to actual concrete shear stress. So we don't test for it in the field, okay? We have equations and methods and procedures that we design for shear in concrete structures, but we don't actually check it against concrete allowable shear. Okay, having said that, lightweight concrete shear factor, lambda, okay? So circle this. It took me a couple of hours to find this little booger in 500 pages of code. It's not that easy to find. So these sections that I give you are actually quite valuable because it'll save you a lot of time trying to find this stuff. It is found eventually in section 19.2.4.2. And what the code says is if the density of the concrete is an all lightweight concrete, then your density is basically less than 110 pounds a cubic foot, then your lambda is 0.75. All lightweight concrete, what that means is that your aggregates are lightweight aggregates and your sand is a special lightweight sand. That's how you get to less than 110 pounds a cubic foot. If you have what's known as sand lightweight concrete, And this is kind of a cryptic code, but what this means is the sand is normal weight, the aggregates are lightweight. If you have this, then you have a density somewhere between 115 to 125, and your lambda is 0.85. Or you have what's known as normal weight concrete, where the sand is regular and the aggregates are regular. This concrete is usually about 145 to 155, and your lambda is equal to 1.0. You can basically ignore lambda if you're looking at normal weight concrete. You can linearly interpolate between these classes. The code says that you can linearly interpolate based on volumetric ratios of lightweight aggregate to hard rock aggregate. So you can't really do that if you don't have a mixed design for what they intend to use. But that's how it works. Okay, any questions? That basically covers the material of concrete. Any questions on concrete? Okay. Well, reinforced concrete design uses concrete, but it also uses reinforcing, thus reinforced concrete design. So the reinforcing portion of the show usually comes from reinforcing steel. And I say usually because there are other things. There's pre-stressing strands, there's post-tensioning strands, and there's this whole new field of carbon fiber laminates, and so there are other things, but 99.9% of concrete is reinforced with reinforcing steel. Reinforcing steel is covered by a specification that is published by the American Society of Materials and Testing, ASTM. So ASTM every periodically comes out with a new set of standards. The 4 volumes of the ASTM standards, just the ones in the building industry are probably about 18 inches wide with all the standards. And that doesn't even cover all the ones you need for the building industry. So there's a lot of ASTM standards. So I'm not going to name them all. There's just a few that kind of stick out to our conversation. And those are ASTM A615, which comes in grades 40, 60, 75, 80, and they just added 100. So these grades represent in KSI the yield strength of the rebar. Okay, that's not the ultimate strength, it's the yield strength of the rebar. And A615 are known as plain carbon steel reinforcement. These basically achieve their strength by iron and carbon. And there's a few alloying components to it, but not very many to comply with A615. Then you have what's known as A706. A706 comes in grades of 60, 80, and I understand 100 is in the works. But right now we just have grades 60 and 80. A706 is what's known as a low alloy steel. A706 used to be known as A706W, which stood for weldable. So A615 is actually weldable, but you have to be very careful about it. You have to qualify the welding exactly how you're going to do it to make sure you're not going to get cracking. This type of rebars is more prone to cracking when you do the welding. And you usually have to employ preheat or other techniques to prevent undesirable cracking, mainly. Whereas A706 has less carbon in it. It has more of these other elements in it, most of which I cannot even pronounce, but things like molybdenum, molybdenum. See, I can't pronounce it. Vanadium, chromium, a little bit of copper. There's all kinds of stuff that's in the A706 that helps it achieve its yielding stress without raising the carbon too high. And that makes it more weldable. Then we have what's known as A955 in grade 60, 75, and 80. This is your stainless steel. You might, maybe, possibly ever see this in your lifetime. Maybe. Depends on what industry you get into, if you get into reinforced concrete design. I've seen it once. And I've been doing this over 26 years now. I've seen stainless rebar once. It was crazy expensive, and they used it in a wastewater treatment plant because they were very concerned about, obviously, corrosion. So I've seen it once, but there is, it is out there, and there is a spec for it. And then we have this new rebar spec. This is relatively new. It's A1035. It comes in grades 100 and 120. So this is some good stuff. And it's known as chromium alloy steel, very high strength. And you don't even get anywhere near this stuff with a welding electrode. It'll just shatter on you, basically. But this is slowly being accepted by the code. There are applications in concrete design when you can use high strength rebar like this, and they're slowly adopting provisions to be sure that if you use high strength steel, you don't get other undesirable, like too much cracking or things like that. So that's it. These are the 4 specs that cover all the reinforcing steel. Reinforcing steel, if I was to actually test a coupon of some good old A706 now, and it was 60, grade 60, then it might test out something like this. If you pull it in tension, or if you compress it in compression, it's basically the same either way. But when you start pulling it in tension, you have an elastic range on that rebar. And then you have this yielding plateau, which sometimes you do, sometimes you don't. Some rebar doesn't really have a well-defined yielding plateau, but most of them do. And then you get to a certain amount of strain and it starts building up again in this strain hardening range. So this blue line represents a typical testing coupon of what you might actually see. The red line represents how we treat rebar in design. Very different than the real rebar test is how we treat it in design. Okay, so these are the ranges, the elastic range, the yielding plateau, and the strain hardening range. Okay, but in design, we design it, it's called a bilinear curve. It really has 2 portions. It has an elastic range, and then it has a yield. The yield is assumed to be at the grade of the rebar. So if the rebar is grade 60, then it yields at 60 KSI. You don't see an ultimate strength on this curve. We don't design to a rebar ultimate strength. We only design to a rebar yield. And it's assumed that it will just yield forever in terms of design. You have Young's modulus for the yield portion. And let's see. Okay, so the blue line represents the possible actual rebar stress strain curve. The real curves can vary significantly, so they can have all kinds of shapes, but this is a typical shape. The red line represents the bilinear assumption for concrete design. So again, in design, we never assume the blue line. We always assume the red line for simplicity. and it consists of two segments. You got a elastic portion up to the yielding strain epsilon y, and then you have a flat yielding portion from epsilon y basically to infinity. Young's modulus for steel is 29,000 KSI. That's a fixed number that doesn't change. The yielding strain, epsilon y, is the yielding stress or the grade divided by Young's modulus, which for grade 60 is going to be 207 something. 207 microns, I guess is what that is, or 0.00207 inches per inch. Though ACI 318.14, and from now on, I'm just going to refer to it as the code, does not prohibit using various grades of rebar, it does limit the design value that is used. Table 20.2.2.4a on page 329 of ACI 318 prescribes what yield stress may be used in various conditions. Higher grades may be detailed, but the design is limited to the grades from that table. So you can see as we go through these lectures, you're going to want to have that ACI 318 right there. So you can look things up and you can bookmark them or tag them or whatever it is you want to do. But when I call out these important sections, you want to be able to find those later. Reinforcing steel, hereafter referred to just as rebar. Rebar is kind of a slang for reinforcing steel. Rebar sizes are standardized, right? So that's the one thing in concrete that is standardized. The sizes can be found on table 1.1 on page 25 of your textbook, as well as they can be found in Appendix A on page 507 of the code ACI 318. I reproduce them here. So these are your standard sizes. You have 3 through 11, and then you have a 14 and an 18. One of the classic evil jokes of a concrete professor is to say on a test, what's the area of a number 12 rebar? Ha, 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 ha. And we just laugh because there's no such thing. Why is there no such thing? I don't have a clue. But when they established these sizes, historically, there used to be a number 2, and there may have been some weird sizes in between, but basically those ASTM specs that I referred to, the 615, the 706, those specifications have basically standardized these areas. And what's interesting about it is that each manufacturer of rebar, whether it's Cascade or it's Tamco or whoever's rolling the steel, they can have a different profile of what the cross-section of the rebar looks like. Some of them have slightly fatter ribs on it. Sometimes there's slightly taller ribs on them, but they all have the same area. Okay, so these areas are standardized. Okay, so that's it for tonight's topics. That's tonight's lecture. We'll get into some other fun stuff when we get to these different pieces. That was just an introduction. Each one of these lectures, just before the class starts, I will post these lectures. It's a PowerPoint presentation. So if you're on a Windows-based machine, you can download these to your machine and you can follow along if you like. But each one of these will be posted to Blackboard before the lecture. Again, each lecture will be recorded and posted to YouTube probably the next day. And that's how these classes are going to go. Do I have any questions for tonight? Anybody at all?
Can you show us the book again, Professor, for ACI?
Sure. Let me stop sharing. All right, now I can kind of see you guys. Okay, so that's the ACI code. Now, this is published by the American Concrete Institute, ACI, right? And they sell these books because they want to make money. And it's probably not a very cheap book. So I'm not sure what options you have through the bookstore or through plagiarism or copyright infringement, or I don't want to know. But it is worth getting a copy of that. I think the bookstore does offer it. I'm not sure if there's like a student rate or something like that. If you find an older version, most of what we're going to be talking about is in the older versions, especially the the foundational stuff, but it's not going to be in the same sections as what I refer to. It's not even going to be in the same chapter, because the chapter organization that they had from the 70s until 2011 was radically changed for 2014. 2014, they reorganized the whole book. And all of us who've been using the older versions really had to struggle to find anything in the reorganized version of the book. But again, one way or another, I think it's really important that you have that code book. But if you had to choose between the textbook and the code book, the textbook is mandatory for this course. You're going to need it because all the exams are open book. The code book is recommended, but highly recommended. It's very valuable to have that as well as the textbook. So if that makes sense.
Okay, thank you.
Sure. Any questions for me for tonight? Okay, we're going to close it out. Don't forget that next Tuesday is our next lecture starting at 5. And starting on Tuesday, I will open up a Zoom for office hours starting at 4. Again, if nobody shows up within a half hour or so, then I'll close it out and go get something to eat or something before the class starts. But if you want to, at any time, between now and the end of this course, log into the Zoom for office hour, and you can have more personalized attention that way. Look to Blackboard. I post up information there. Right now the syllabus is there and this lecture is there. And as I mentioned before, once I post these lectures to YouTube, you can find them by just putting in my name, which you can see from the syllabus or on the screen. My name is spelled E-R-I-N, so type in my name. And then there's quite a few Aaron Pratts on YouTube, believe it or not. But put in some kind of a keyword like engineering or CE 4510, something like that, and I'll get you to these lectures. Okay, so if there's no other questions for tonight, we will see you on Tuesday. Everybody have a great weekend.
Thank you, Professor.
Thank you.
Professor.
Sure.
Have a good one, Professor. Thank you.
You too. Thank you.
Professor.